Hello and welcome to the second part of the tutorial on writing the Raytracer and Common Lisp. My name is Alexander Lehmann, and during the second part I'm going to introduce you to basic ray tracing. The last time we've almost finished the linear algebra package. I say almost because during testing I found out that maybe we should make some improvements and at least one necessary addition also. Then when we get to the point, we will talk about the camera and the image plane. We'll also talk about world and view coordinates. And later on, before doing our first actual ray tracing, we of course have to talk about the intersection of a ray and a sphere, as well as of the intersection of a ray and a cube. Okay, so you see ASDF and ZPNG following also. We'll use those packages, ASDF basically for installing ZPNG, but also for defining and maintaining our inter-file dependencies, because we're going to create a lot of files today. And yeah, ZPNG, we'll use that for being able to export our resulting images as PNG files. Okay, so let's hit the road, go back to our linear algebra source. And the first thing that I would like to do is go back to the m* method. We've defined a few methods called m* for the multiplication of matrices, and also matrices and scalar values. Whatever. However, what we forgot, if we wanted to evaluate a form like this, m* 3.0, 4.0, a, b, 5.0, something like that, with the code that we have written, we can compute 4.0 times a, and a times b, and b times 5.0. However, we cannot compute 3.0 times 4.0, and this is of course something that we would like to do. So we define another method, m*. We'll specialize that on a as being a single float, and b also being a single float. We return the sum of a and b. That's it so far. And also, if we take a look at our multiplication of two matrices, there's one special case. Imagine that the matrix A has only one row and that the matrix B has only one column. Then our resulting matrix will have only one element, one total. And in this case, the multiplication's result is a scalar value. So after we have done this do matrix stuff here, we might want to check if the resulting matrix, so if has only one column and one row, and in this case only return the element inside of the matrix data array, or else we just return the whole matrix. So if and the number, or we can just use one equal sign here, if 1 equals matrix columns result as well as matrix rows result, then I said we return matrix, let's make this faster, aref matrix data result 0, or else just return the matrix. Okay, we're done with that. Okay, maybe we should now take our time, start up Slime, hit meter X, enter Slime, enter once again. Okay, go back to the source and compile it. I bet we're going to have a small warning, but we'll get to that. Control C, Control K, exactly. Style warnings about a undefined function m*. Hit Q to get rid of that warning and maximize the window. So the reason is fairly simple, as well as the solution. We just have to provide information about m* and its lambda list. So def generic m*, and all methods that that belong to this generic have a lambda list of 2 operands, and that's all. Okay, going to compile that once again. Of course, again, we're getting a lot of style warnings, but these are only due to the fact that we are redefining a few functions, or actually it's all functions that we redefine. The next time you start up Slime and compile in-alg, you'll however see that we got rid of this m-star related warning. Okay, talking about m-star, you see that we specialized a few methods on real values. Real is basically a super type of floats and rationals in Lisp, and normally we don't want to deal with rationals, and we can also help the compiler to improve the code in order to get faster code by narrowing this down to single floats actually. Once again, this is not necessary, but this only helps the compiler to produce faster code. And of course, in our linalg package, we're interested in very fast code. Okay. So I've replaced the reals with single float. Let's see if there is another thing like this. No, there isn't. Okay, then I would like to make sure something else. Go to the beginning and look for all occurrences of the function map. We've used that quite a few times. So the first argument to map actually is the result type, the type of the result. And in our case, this is not only a vector, but this is instead, or we want instead, a simple array whose element type is single float and whose rank is 1. Again, this is not necessary. This just helps the compiler to make faster code. Look for the next map. Map in 2 doesn't create a new array, but here we have the same problem once again. Simple array, single float, rank 1. We're done with that. No more maps, I think. Yeah. Okay, good. So then almost the last thing is we have defined as a nice macro, make vector in order. So if we just want to create vectors, then there's no need of specifying all this make instance, matrix, rows, columns, whatever stuff. Instead, we just want to have this convenience macro make vector, which gets only the dimension and maybe the orientation or generator function. What we forgot, however, was providing a data keyword. And so if here we have the data keyword, we also want to have this expanded for the make instance method of the matrix class. So here we check if data has been provided, then we'll return data, and instead we'll check that when a generator has provided, use that. We reformat the source code here a little bit. Okay, this would be exactly the same. We return data, or else check once again if a generator has provided and return that. Okay, so compile the whole thing. Let's make a small check to see if this works as we expected. Make vector. Let's say 10 is maybe much 5. And orientation, we don't need that right now, but we want to make sure here data 1.0, 2.0, 3, 4, 5. Now we hit Control C, Control M to see what this macro expands to, and expands to make instance matrix rows 5, columns 1, data. Nice, that's what we wanted. Hit Q and test the second case. Use the generator function with only one argument in this case. You remember that here we wrote a closure lambda k, and let's return 15.0. See what this expands to. Again, exactly what we wanted. Okay, delete this line. Maybe one thing, if we go to the mult method, you see yeah, there's a lot of fuss about imperative versus functional programming. Here we are using a loop-like statement. Of course, the yeah, let's say more Lispy way would be to define the whole function slightly different. I'll show you how. So we'll start with an accumulator and say rest operands, and then we check if the operand is a non-empty list, and if it is, we apply to the function mult, and the first argument will be the result of multiplying the accumulator by the first of the operands, and then the rest will be the rest of the operands. Okay, and this, if instead the operands is an empty list, we'll return the accumulator. That's the recursive solution. So the basic case is the lower one, and this is the non-basic case, the recursive solution. However, this brings no speed improvements or whatever. We'll just leave it as we have had it before. Okay, Control-C-K, compile it once again. I think that we are done with the linear algebra package, at least for now. So we might want to start with the basic ray tracing stuff. And why not start out by defining a camera? Okay, so go to camera.lisp, and let's make sure, yeah, we need some, okay, however, we'll need another file where we define the package, or no, let's just define a camera package here. That's maybe just the easiest. Call it CLRT camera for Common Lisp Raytracer camera, and we'll use the Common Lisp package, and we'll also be using the linear algebra package. Later on we'll have to export symbols. Okay, that's later. Okay, this is the first point where we encounter a possible use for ASDF. You see that we use the linear algebra package, and in future times, as I said, we'll have a lot of files and a lot of file dependencies there, and why not let ASDF handle all this, so that the next time we return to Slime and Lisp, we can just use something like require CLRT and be happy with ASDF loading and initializing all the necessary stuff for us. So I'm going to open a file CLRT ASD, and this file is ASD. We'll make sure that we are in Lisp mode. This file only contains let's say we require ASDF at this point, and we'll define a package, a system, a so-called system. So we say ASDF def system. We'll call our system CLRT, as I said, for Common Lisp Raytracer. Now we can get a short description here. CLRT, a simple Common Lisp Raytracer. A lot of more keywords. We'll have to depend on a few things. Okay, why not right now add ZPNG, for example. And of course, we also have a few components, which basically are our own files. Start a list, and the first file is just linalg. Linalg doesn't depend on anything else, so I'll just close the parent here. But then we have the file camera, and the camera itself in turn depends on linalg. So that's it so far. Okay, let's go to the REPL and try this. Require CLRT. Very nice. We got an error. No dispatch function. Where was that? Must have made a big mistake somewhere here. ASDF def system CLRT description depends on, so okay. Maybe this is just due to the require here. So this once again get a big error on the stream source CLRT ASD. Yeah. Okay. Very easy error actually. Yeah. this is the problem. Those sharp signs and the following signs are often used as so-called reader macros for the Lisp reader, and because I forgot the colon, Lisp didn't know what to do with a macro sharp sign and Z. So if I make this, we'll be fine. SDF require CLRT. So component ZPNG not found, required. Okay, this is very clear. I forgot, I wanted to show you how to install packages via ASDF, and that's what we're going to do now. So we require ASDF install, and then we use ASDF install to just install the ZPNG package. Hit enter here. Now it asks us where we want to install the package, and I prefer the personal installation. So this error is expected. Usually you should really see that you get the GPG keys of the package maintainers, and never do what I'm going to do now, but I'll just skip the check by hitting 0, and this will happen once again, I think. Yes, this is due to the fact that ZPNG in turn depends on Salsa2, the library Salsa2, and they were both now installed on the system. Let's go to the REPL once again and require CLRT, and now this should work. Yes, it did. You see, it compiled the CLRT camera stuff. Very nice. Okay, so I'll just leave this in the background and return to the camera. And the camera package, of course, what can we do but define a camera class? The camera in our case will be defined through, or will have several slots. First and foremost, of course, its position, but also its direction and a so-called up vector, because we must know a little bit more about the camera's orientation. Okay, that's it. And the position, we'll provide a init argument for that called pos, and throw an error if this wasn't provided. So pos must be specified. So and pos must be of type matrix. We can safely use this type here without preceding it with linalg colon, because we have used all the symbols that are exported by linalg here. Okay, that's it for the position. The direction will also get an init argument till inform. You know what, we'll neither provide a init argument nor a init form for it, but only the type matrix. And up, however, we need a init argument for that. Up init form, up must be specified, also of type matrix. Okay, so of course we need some way to initialize our matrix. As before, as we had it with the matrix class, def class defines a few generics and also methods for us. First and foremost, initialize instance. We'll use initialize, we'll extend this a bit. So def method initialize instance. We want to go after the original initialize instance method that was declared by def class, and our arguments will be specialized for let's call it cam, which will be camera, and we'll have a keyword called lookAt. Okay, so something else that I just see, the camera has one more property basically, that is the so-called field of view. Just call it FOV. Also get an init arg FOV, and our default value for that will be 110 degrees. Now comes a nice Lispy thing here. We can specify the type in a way that we say, okay, this is going to be a real number or a integer or whatever. We'll use real number in this place, and it must be between 45 and 130 or so, let's say. Let's just 70 and 130. These are reasonable values. Once we get to the point where we talk about the image plane, you will soon see what the field of view exactly is. Else I suggest also looking it up in Wikipedia or something like that. Okay, so here at this point, the position we don't have to do anything about this, but the direction will be defined. We'll use the look at, because also we expect if someone calls make instance camera to provide the look at keyword and provide coordinates via make vector 3 and data. This is just an example. Look at the point 0, 0, 100. We want to compute the direction automatically depending on the position of the camera. So at this point we say setf of we should also define an accessor function for that here. Make this a reader. Oh yeah, actually we could also, yeah, let's make this a whole accessor camera direction. Okay, so setf camera direction cam. We could also, instead of using the successor function, we could use the slot value function. So setf camera direction cam, and yeah, maybe we should even do this because we don't want to have the outside world be able to modify our camera direction. So we just make this a reader and say use the slot value instead. Slot value, the object is the camera and the name is direction, and we'll set this to a normalized version of m minus of the camera position. Okay, this therefore we definitely need a reader. Okay, let's call it camera pos minus the value provided by look at. Okay, so as I said, we need a reader for this. So reader camera pos. That's it so far. We should not forget to export the symbols. So the first symbol would be camera, and then of course camera position as well as camera direction. Don't have anything more like that right now. Okay, I think that's it so far. Let me get rid of the last superfluous lines here and maybe just compile. Have an unmatched bracket. Okay, one more. Compile the whole file. CK. Get a lot of style warnings. Undefined type. Real. Okay. Don't want to mess around with that right now. Maybe this could be the solution. It is not. Okay, in this case, I don't know the solution right now. We could look it up in the hyperspec by, this is a nice feature, I might show it to you. It's like you hit Control C, Control D and then H, and then we get into the hyperspec. We could look up anything we wanted to know about specifying a type here. However, I just return to the source and not read through all of this and waste my time on it. So just forget about the type. You could, yeah. I'm very sorry for all this mess, but let's make it type single float instead. we'll notice soon enough if this is not okay. Undefined type matrix. Why is that? Actually, should know about the linear algebra package. Set dev package CLRT camera, and we are in that package. We are importing the symbols from the linalg package. Linalg, if I compile that, return to the camera, compile that. Very sorry. Let's see. This didn't help anything. Okay. This is a nice problem here. Of course, we could solve it by just preceding all the occurrences of matrix with linalg, and that's what we'll just do right now. Maybe I'll come up with a solution later. I'm pretty sure this is a very basic problem. However, undefined type matrix. That once again. Okay, I'm getting really annoyed by this. And yeah, of course, this is the answer to everything. This macro expects the type to be unquoted. So if we use matrix here and matrix there, as well as matrix here, compile it. See, there's no error, no warning. This should be the same explanation as why our type specification for the field of view didn't work. So let's try this once again. 70 up to 130. Must close something. Oh yeah, okay. That was one parent too much. Compile it once again. Again, get an error. But this error must be related to a parent. Something. Yeah, exactly. Okay, here and here and here, and there we need one more. Compile it. Very nice. 0 errors, 0 warnings. So the problem only was related to the type being quoted or not. However, we're done with that. And okay, this is so far all that we can do for the camera right now. We should now switch and take care of objects instead. So we'll open a file called objects.lisp. Again, define a package for that called CLRT objects. We'll be using CL and of course again the linalg package. And later on, so we should export the symbols. Okay, whether or not to use a sharp sign at these points is a matter of taste, since we actually just need a name specifier, and yeah, the one that consumes less memory is the one with the sharp sign, but forget about that. Okay, so all objects will have a certain superclass called object, which in turn doesn't have a superclass, and every object has of course a center, and every object has a material as well. Okay, the center get an init argument, init arg, and this again must be specified. Center must be specified. Okay, it will be of type matrix. Okay, now don't use the Gorham quote sign. Material. Yeah, I'll see to it once we get to that. We of course have also to define a material. However, I'll at first stick with the object class. And also, we shouldn't forget to add the file objects.lisp and all its dependencies to our ASDF system definition. So I return to this and I say file objects depends on linalg as well. Okay. Yeah, that's it so far. Return to the objects. And at this point, I'd like just to define a generic and a corresponding lambda list for a method called intersects. This method will have two arguments, or actually no, it will only have one argument, and that will be array. Maybe we'll need a few more later on, but right now only this one. And also we want to have a generic called finalize, and this finalize method should have two arguments, the object that we want to finalize and camera. And talking about finalize, forgot the object and the lambda list of the intersects generic. What we after defining the generic, what we can do is define a finalize, which is specialized on our superclass object. So object will be of type object, can will be of type camera. Okay, so there's another dependency. Make a break at this point and add the dependency. So we'll also depend on CRT camera and go to our ASD file. And okay, so this depends not only on linalg but also on camera. Return to the objects.lisp file. Very nice. So what we can do right now, yeah, actually I was a little bit too quick. We cannot do very much until we have talked about the change between the transformation between world and view coordinates. So in this case we'll just return t and fill out the body of the method later. Okay, so the next thing that we need is obviously a scene where we put all the objects, all the lights, and the camera, and all the information that we need. So we create a file called scene.lisp. Again, define a package, maybe this time crt scene. We'll be using cl, we'll be using camera, and we'll be using objects. Of course, we'll also be using linalg. Go to the ASD definition and add scene, which depends on linalg, camera, objects. Okay, and maybe again, sorry for the mess, forgot to export some symbols here. I've exported almost all necessary things. What we're going to need in a few minutes is also access to the field of view of the camera. So from this camera FOV and export it as well, camera FOV. That's it, compile it. Then we'll head back to the objects. Here we completely forgot to export any symbols. Every object, the center and maybe the material, we might need a reader for that. So we just call it object material, and we'll export the symbol object and of course object material, as well as intersects and finalize. Compile this. Now we return to the scene. My apologies. Make sure we're in the package, in package scene, and again start out by defining our class scene. No superclass in this case. Now let's think about what we might need. Every scene has a camera, Every scene has a certain number of objects. Later on we'll need lights and so I'll just add them here, although we're not going to use any light related things during this second part of the tutorial. Yeah, that's it maybe. Okay, the camera, special argument for that, init arg will be camera. We need this to be specified, of course. Init form error camera must be specified. I wonder if we could use a macro for all this repeating stuff. Init form, the type will be camera. Yeah. Reader for that. Scene camera. Okay, so far so good. The objects, no init argument for that, so but we'll need a init form, just an empty list. The reader scene objects. Yeah, and we'll just do the same with the lights. Init form reader scene lights. You might wonder why I'm initializing objects and lights, both slots, why I initialize them with an empty list. The thing is that if I leave these slots unbound in any fashion and I try to access them via a slot value, I might run into trouble. And a case where this could happen would be something like this. We say def method. Of course, we want to be able to add objects to a scene, so def method add object, or why use a method? Function is suffices here. So defun add object scene and the new object, and now we'll just push the object, and the place will be the slot value of our scene, and the name of the slot is called objects. Okay, not to forget, we have just created a few symbols, the first one being the scene, the second one being add object. Now let's try and compile the file, get an error. The name camera does not designate any in package. Why is that? We are using the camera package, and I think we have, maybe go back to the camera file once again. We have exported the camera symbol, compile this once again to make sure that this is really exported and that the symbol exists. Then we go to the scene and compile this once again. Again, get the error. The name camera does not designate any package. Okay, my mistake. The name of our package is CLRT camera as well as CLRT objects. Let's see if we've done that correctly in objects. Yeah, there it is correct. And in camera itself, yep. Okay, so go back to the scene, save it, compile it, Control C, Control K. Very nice, 0 errors, 0 warnings, 0 nodes. We're happy with that. Okay, so I'll go back to the slides. Now we have to talk about the so-called image plane. The image plane is actually just, will hold our final image in the end. The image plane, however, will not have extensions like 640 times 480 or something like that, but just be a rectangular plane in space. And it will have certain extensions, and of course we're interested in those extensions, like the width and height, of course. Okay, so the half circle here denotes the camera or the eye, whatever you like to call it. FOV is the field of view that we mentioned earlier. Now you see that the field of view is just the angular extent of all that we can see from our viewpoint here. delta here is just 1/2 of the field of view. We'll see it in a few seconds why we need this delta. Okay, so our camera provides us with the FOV, and we also know a certain other thing. We know the distance from our camera to our image plane. This is an arbitrary distance. However, we make this distance constant in our case. We just say that A is 1, so wherever on this slide you see the variable 1, you can safely replace it with wherever you see A, you can safely replace it with 1. If we want to calculate the width of the image plane, however, the only way we can do it is via the geometry related stuff you see on the right hand side here. So the whole triangle covering the whole image plane and everything has no perpendicular sides, but we need this in order to be able to work with the sine and cosine. So this is the reason why we split this outer triangle in 2 halves. It is arbitrary whether we choose the left or the right one now. Let's just stick with the right one. Delta, as I said, is just 1/2 of the field of view, and now it's very easy to calculate B. The whole width will of course be 2 times B, but 1 times B is as follows. We know from geometry that the sine of delta equals B divided by C, and also that the cosine of delta equals A divided by C. And if we solve all this for B, we get something like A times sine delta divided by cosine delta. And now we know that sine divided by cosine is nothing else but the tangent. Also, we could replace, as I said, A with 1, and thus in the end the solution is B equals the tangent of delta, which actually in turn is 1/2 of FOV. So the width of our image plane can be calculated as 2 times 1 times tangent 1/2 of FOV. And yeah, okay, let's see. Here we have another ratio that we need, and this is to compensate for the aspect ratio. Usually you have images in with dimensions like 640 times 480 or 800 times 600 or whatever. And to be able to compensate for that, we divide the height by the width and multiply it by the width. Actually, this is the width of the resulting image that we want to have, and we'll have to multiply it by the width of the image plane that we have just calculated. So let's go back to the source and define everything that we need for the image plane. Yeah, we might also consider declaring a function called render. And the first argument for render will be the scene, the second argument maybe the width, third the height, and the fourth and last the name of the output file. This is where we will make use of ZPNG for the first time. Let's say that image is an instance of ZPNG image, where width and height equal the parameters that our function render got. Okay, that's all we need right here. Then if we want to access the underlying data of the image, we use image data, which is a ZPNG data. Okay, I have to use okay, no completion right now. ZPNG, I think it's data array or something like this. We could go and inspect ZPNG. Yeah, maybe that's a nice nice possibility for that. So we say inspect, and we want to inspect symbol ZPNG. see if this works. It is a name. It names the package. So okay, we go to the package, hit return, and see that yeah, it's useless. It uses Common Lisp and Salsa too, and it has 9 external symbols. And we are only interested in those external symbols. Go there, hit enter once again, and now we see, okay, the functions exactly: data array, image data. Yeah, PNG is the class. You see that by those flags here. Okay, data array was the one that we wanted. The function can go pretty deep in this. There's unfortunately no method documentation in here. Just hit Q and return to the source. I think that's enough. However, I know from memory that the one and only argument for data array is the image. So we'll use that here. And now it is time to compute the extents of our image plane. So we say that max x is, just go back once again to see, okay, we have the whole image is 2 times, but yeah, since we're starting 0 is in the middle, so we just need b, and this is actually just tangent of delta. However, we have to pay attention to the fact that we do not mix up radians and degrees. So at first we need yeah, okay, we make this delta, and delta is the camera field of view of the scene camera of the provided of our scene. Okay, so and now this has been given in degrees, so we have to divide it by 360.0 and multiply everything by 2 times p. So and okay, so we see that we can remove the 2 and replace it with 180. That's fine. Okay, now our max x is just a tangent of delta. Min x is just negative max x. Max y, as we said here, we have to correct for the aspect ratio. So we have to multiply max x by let's see, height width. I want to make sure that these are single floats. So let's say coerce. Coerce can be used to convert types. So we convert height to single float. Do the same with width. Okay, and min y again is the opposite of max y. Phew, that was a lot of stuff. However, now we are able to iterate over our image plane and collect all the results from the rays that we are going to shoot, the resulting colors, and put those resulting colors in the image. So if we now want to iterate over the image, we would say something like 2 times, or we might want to use do instead of do times do. Okay, and the variable that we are going to use, the first one, is our actual row, or let's call it y, the y position, and y will be initialized with min y, and okay, I just see that we need to calculate the step sizes for both horizontal and vertical steps. So, but let's finish this first. Let's say plus y step y. So this is the first and only variable in this case. Our end case will be that y is greater than max y. So okay, in this case we're building it bottom up, the image, whatever. Okay, and yeah, in the result we return right now, let's just return t. Okay, that's the first two. The second one will be, we'll have x, initialize it with min x, and x plus step x. So the end case here is when x exceeds max x. Don't have to give anything back here. Okay, so now the point on the image plane that our array will first aim at when it is shot from our eye onto the image plane or through the image plane will be, we'll have another LED here, or we could also use this and place this in the do part. Yeah, why not do it? Okay. So we say that the second variable that we need will be the ray's direction, so we call it ray dir, or maybe, yeah, let's call it ray dir, and it will be initialized with a 3-dimensional vector. And yeah, okay, so we need this to be very fast, so we say make that's what we had, make array 3 element type single float, initial contents will be vector in x, in y, and 1 because we said that the distance is constantly 1. So that is the initial form, and else also data array 3 element type single float initial contents. This will be a little bit more elaborated or sophisticated or whatever. This is actually very easy. This is just a vector of x, y, and 1. Nice. Okay, so we could use the same here, x, y, because they used if I use do star. So, okay, that's fine. Need one more parent here. Don't return a thing. Yeah. Okay. So just choose Terpre here and do nothing, because we can't do anything right now. However, let's first see Control C, Control K if this compiles. Yeah, but it says there is one error. Let's see. Where is it underlined? The variable file name is defined. Okay, that is obviously only a warning. These are also only warnings. Yes, exactly. Step Y and step X, I forgot about those. So step X is just 2 times max X divided by the width. Also make sure that this is a float. The same with the step Y times max Y or single float. See, compile this once this again. Still have an error. Step x is defined. Okay. The step variable is not a symbol. How's that? Okay, my fault. This should be one more parent here, one less there. Compile it. We got rid of the errors. However, the two style warnings remain, but they are only related to the fact that we haven't used file name or image data. What we can do right now is, in the end, after everything, we don't need a true here, we don't need that anymore. We want to write the resulting image. Again, I don't know the exact function name, and let's see if we go zpng and hit the tab key, what do we get? Write png is the name of the function that we are looking for. Okay, we go back, zpng, write png. Okay, now at least now we get the parameters. And it's our image. The path name is just the file name that we were provided with. And as far as I know, if exists is just given to the related with screen macro. So we just say if the file exists, and we want to supersede it. Compile it, got rid of at least one of the style warnings. Let's see the last one. Of course, image data is defined but never used. You know what, we just see if we can yeah, there's another thing. Maybe we should, instead of using x and y to iterate over the coordinates of the image plane, we should use x and y to iterate over the image coordinates, and instead use x and y to calculate the position on the image plane. That is fairly easy though. Okay, so if we wanted to do that, we'd say that y begins, for example, at, okay, now we have to pay close attention. Now we're also converting it to computing the image upside down, or yeah, actually it's not upside down, but from the top to the bottom as we're used to it. So we begin with 0 and 1 plus y. So that's it for this here. Okay. The whole thing will terminate once y gets greater than the provided height. Here we'll do the same. X starts out at 0, will be increased in every step. Now there's the thing, our coordinates are now different. We cannot call them xc, for example, or x coord. That's the coordinate on the image plane, not on the image itself, but on the image plane. And this is the result of adding min x plus x times step x. The same for the y coordinate. That's the result of adding min y plus y times step y. So we can replace the x coord and the y coord here. Okay, this is okay. Let's see if this compiles. Yes, it compiles. So now, instead of doing this ter-pre, we can, for example, write just the blue value to the image data array. So we say setf aref image data, and at first I know from zpng comes the y coordinates, so we say y and x, and then depending on whether we want to write the red, green or blue component, we said we wanted to write the blue. This is the last one, so this is going to be 2, and we'll just write 255. Okay, compile it. very nice. So let's see if it works. We have the scene package. So if now we wanted, yeah, there's a little bit more. Since we need the scene, we also need a camera and stuff. And yeah, okay. Let's see. Let's go to the REPL. Let's define a camera. The parameter instance of CLRT camera, and we know that the keywords are pos. We need to initialize a position, say make vector 3, and data will be 0.0, 0.0. Okay, that's enough for the camera. We also need a up vector, that will be 0.0, 1.0, 0.0, and of course the position that we're looking at, make vector 3 data. Okay, just straight ahead. That's our camera. Okay, let's see if this works. The function make vector is undefined. Yeah, that's clear, because we didn't use the package linalg in the REPL. Okay, I'll just go ahead and use the package linalg. Probably we'll get an error about conflicting symbols. Yeah, exactly. We solve it in favor of linalg make vector and repeat our last command. Def parameter camera. Okay, very nice. Just to make sure, we don't want to find the definition, but instead we want to inspect it. Its name is camera, and it's a global variable bound to the camera. Okay, the direction, matrix, the field of view, 110 position. Let's see. That's basically not the right direction. So go to the camera once again. And yeah, we have to do it vice versa. We have to subtract the camera position from the look at position. Compile it once again. Go back to the REPL. Def parameter again. So we go and inspect it. Go to the camera. Go to the direction. And now we see, okay, it was computed correctly, being x0, y0, and z 1.0. That's what we wanted. Sorry, I used the wrong key. Go to the camera once again. FOV position is 0, 0, 0. That's also very nice. Okay, and the last thing, I forgot the keys to go back and forth. Is the up vector. That's also what we wanted. Okay, so far so good. This is our camera. Now we are going to define a scene, make instance CLRT scene, and the argument will be the camera, being the just defined camera. And as far as I can see, nothing else right now. Def parameter scene. Okay, so why not try CLRT scene render? Provide the scene. It will be 640 times 480, and the file name will be test.png. Let's go. Okay, simple reader package error. The simple render is not external. Yeah, that's typical bug of mine. So we go back to the scene, make sure that all the right symbols are exported. We are especially interested in render. Compile it once again. Use render. The value is not of type single float. Yeah, okay, that's a problem that relates to the tangent. The tangent obviously returns a double value. So let's see. Where do we use the tangent? We use it here. Maybe we can use coerce to convert this to a single float. I'm not exactly sure about that. just try. The value 1 is not of type single float. Now we really have to see. Yeah, this is when we multiply. Here we have to use 2.0. We have to be really sure what types we are using. And here the problem is that we initialized with 0, so Lisp thinks that we are dealing with integers instead of floats. Maybe this should be enough. Let's compile it. Okay, we get an error here saying deleting unreachable code. Why should this be unreachable? I really don't know. In my opinion, 1 plus is just a synonym for plus 1.0x. Maybe we should prefer this anyways. Plus x 1.0. Now, here we have the problem that we need integer values once again. So you see, if we had stuck with not typing anything, we wouldn't run into problems right now. However, we decided to do so, so we have to solve this. We can say trunc y and trunc x to get rid of the problem, I think. Let's see, Control C, C compiles this function. There's no trunk, I think it's called round. No, but hey, why not look it up? Control C, D, H. So we see that we have floor, ceiling, truncate is the name. We're going to use truncate and not round. Save it, hit Control C, C once again. Very nice. 0 errors, 0 warnings. Anyways, that's just what the compiler says. Let's see what the REPL says. If we now go ahead, again, the value 1 is not of type single float. I have no idea, however, where this value originates from. Here we see that I know where it originates from, exactly here. Yeah, that's again due to the strong typing that we're using right now. Compile it once again. Okay, that's it. Now it worked. Again, sorry for the mess. Let's see what our image looks like. We execute a shell command. Open test PNG. Okay, you don't see it. I work on a dual screen system here. However, everything is black. That's also not what we wanted it to be. We close the image, go back to the source, and let's now see why this could be the case. So everything here, we initialize the image. It's only possible that we're not that our loops don't execute like we expect them to do. However, we could, yeah, printing all those coordinates would be a bit much. But what we could do instead is just see at least if zpng works. We could say do times I 480. Times j will be 640, and with ZF image data I j2 to 255. Then we'll go and get rid of all of this here. So we string insert rectangle, comment this out. This okay, this is okay. Compile this function once again, go back to the REPL and execute. Now let's see if the image looks better. Yeah, exactly. Everything is blue, so the error was in the use of, or relates to the use of the use macro. Go back and undo all this stuff here. let's see. So what happens here? We have compile it to get rid of the warning. We have y starting out at 0.0 and being increased by 1.0 during every iteration. So then we check whether this is greater than height, and in this case we end. Okay, this should be this should work. However, you know what, we don't. Let's just revert this and stick with integers. Okay, start out at 0, 1 plus x. Try it once again. So here we stop. Notation is a little bit wrong here. We start with x at 0 and increase x with every step by 1. Then we compute the x coordinate as the result of adding min x time plus x times step x. Do the same with the y coordinate. Okay. Define array that we're not going to use right now, but anyways we have it. And okay, so we'll end as soon as x is greater than or equal to max x. Yeah, this is silly. This is not right. This must be width instead. Okay, let's use green this time to see if it works. If we have a difference, compile it, execute it, open the PNG file, and it's green. Okay, the problem is solved. So our iteration over the image plane works right now. Good. Yeah, so far we have just finished this. We also have to deal with the intersection of the ray that we are going to shoot and stuff. So let's first, I'll go back to the slides. We talk about the differences. First, let's start out talking about the actual coordinate system that we are going to use, as well as the difference of world and view coordinates, and then I'll directly go to the intersection of a ray and a sphere. So the coordinate system that we are going to use is fairly simple. As you can see, our horizontal axis x is x, our vertical axis is y, and the depth axis is z, with increasing height with increasing values, and the same is for z. So this is almost a standard left-handed coordinate system. So just so that we are sure that we're talking about the same coordinates. There's nothing more to this. If now we come to the point where we talk about world versus view coordinates, you can see this is a top-down view of a example scene. So here we see the z-axis going to the depth and x, so we're looking top-down. You can see a few objects scattered around here, as well as a point x. And this point x will be relevant on the next slide, you will see it. Also, you'll see our camera couldn't really depict the up vector here. However, our camera will have 3 vectors in the end, or maybe even, actually even 4. The first one being the position, then its direction, its up vector that's pointing in our direction right now in front of the screen, and also the right hand vector that defines the horizontal axis of the camera. So going to the next slide, you see the difference. These were world coordinates, and the camera itself, the position of the camera, was also of course in world coordinates. It makes things a lot easier if before doing the actual ray tracing process we convert from world to view coordinates, and the conversion is fairly simple. It's just a matter of basis transformation, and the new basis that we are going to use is made up of the vectors of okay, I see that I forgot a exponential something here. It's just the basis is just composed of the vectors of the camera right, up, and direction vectors of the camera, corresponding to our Euclidean x, y, and z world coordinates. So what we are going to do is we first of all have to correct for the displacement of the camera. This is what happens here when we say x minus cam center, or the cam center in this case is the position of the camera. And after we've done that, we want to see what the coordinates of those objects look in the coordinate system, expressed in the coordinate system of the camera. So actually we in this case have to multiply with the inverse of this matrix. I'm very sorry, here it should be raised to the power of -1, as you can see here. That x, let's go here, okay, here we have the point x and x star, which is basically x expressed in the coordinates of the view coordinate system of the camera. X star is computed as the inverse of the basis of this new basis matrix, and the since this is an orthogonal matrix where all those vectors, those camera vectors, are perpendicular to each other, the inverse can be computed very simply. It's just the transpose of the matrix. That is correct for all orthogonal matrices. So the transpose is just as you can see here. The camera right vector being the first row, the up vector being the second row, and the directional vector being the third row. We multiplied by the position that we corrected for the camera's center. Yeah, and that's it. So this is pretty straightforward. This is just, actually it's just easy linear algebra. And so there's one thing that we could use this for. So maybe before I proceed to the intersection of a ray and a sphere, we should go back to the camera package and define a convenience function for us. Let's call it def method world to view. And world to view will have two arguments. The first one being the camera, and the second one being a vector. So type matrix, and okay, it will behave nicely. We also define a generic for that. This just suppresses a warning that we'll get from the compiler, or a node saying that the generic was implicitly created. So we say op1, op2 once again, get rid of that. Okay, we are using the linalg package, so we can use this matrix thing here. However, I would like to introduce another slot called, let's say, world to view matrix or whatever. World to view matrix, or W2V matrix to be a bit shorter. No init argument for that, no init form for that. Type will be type matrix, and the accessor will be W2V matrix. We don't want to export this, but we want to use it ourselves instead, saying first of all, if this matrix has not been we have two cases. The first time we were called world to view is called this matrix hasn't been computed, so we'll do it. And yeah, we can just check if slot bound P of the given camera, and the slot's name is W2V matrix. If this is the case, we can simply return the result of multiplying our matrix, v to v matrix of the camera, multiplying it by the given vector. That's the result. And if not, we have to see that we create this matrix. So let's see. We set up, we make a problem here. We set up the v2v matrix of the given camera to the matrix, make instance matrix. Yep. And we will have 3 rows and 3 columns, and we initialize it with data from a we again want to be fast, so we make an array of size 9, 3 by 3, element type single float, and its initial contents. Yeah, they are basically right. You saw here, its initial contents are the x, y, and z parts of the respective vectors. So we'll use vec x of the right vector. Yeah, okay, now I see another problem. The problem is that we really want to make sure that the vectors that we are going to use are orthogonal, are perpendicular to each other. So maybe instead of starting with this problem, we should make sure of that. Yeah, whatever. First I'll finish this, or else this will be too confusing. So at first we have the vec x of the right hand vector. The right hand vector is not a slot. Yeah, let's just say, okay, of vec x of right, as well as vec y, vec z. Then comes, let's go back, then comes the up vector. So z up, and last the direction. And okay, after we have said that, we also want to return the result, the product of our just created matrix and the vector. Okay. As I said, we want to make sure that everything is orthogonal, so I'm going to replace this program block with a let block here instead. And you see, the only thing that we are going to keep right now is the direction. We're not going to change that. We have the up vector, and now if we want to compute the horizontal axis, we have to compute the cross product, the normalized cross product of the up vector and the, no, actually it's vice versa, of the direction vector. So yeah, we should give it a name. Our new right hand vector will be normalized cross of the direction, so camera direction of the camera, as well as the up vector. How do we call the excessive function? Okay, we don't have an excessive function for that. Let's call it camera up. So times cross product of this. After we've calculated that, we'll also correct the up axis, being the cross product of, let me think, I think the direction and right. Okay, we should have a look into this later on. Okay, go to the REPL and make a test case for this. Let's say v1 will be the direction of the camera. Okay, and this is a matrix vector 3, and its contents will be 0, 0, 0, 1.0. This is our camera direction. Odd number. Yeah, this is clear. We should have provided the data keyword. Then we'll have camera up vector. This is basically nothing else but 0, 1.0, 0.0. So now let's see what the cross products evaluate to. Normalized cross. Okay, if we are dealing with unit length vectors, it should be superfluous to normalize them. However, just to make sure, normalized version of cross, and then we have always crossed the camera direction and camera up. Okay, the result is exactly in the opposite direction. So that's an easy thing. We just have to swap those. Unfortunately, I forgot the key. Emacs can do this automatically. Swap those ZSPs for us. This is, however, now I hope correct. Camera up. Camera down. Okay, this gives us the horizontal axis. And now let's see. Yeah, we want to call this thing right. Cam right is the cross product of cam up and cam down. Okay, and now let's see what happens in the next step. Cross product of cam right and camera direction. Again, the same problem. I have to change that. So cross right and the camera direction. Okay, compile it. See, 3 warnings. That's a lot. That's a lot more than we intended to have. Def method, undefined function. Yeah, that's due to the fact that I didn't compile the def class thing here. Once again, I'll just go ahead and compile the whole file. One warning is about aref. We're using make array. Yeah, that's okay. Element type is single float, initial contents. Here we have an unused variable dir. Yeah, since we didn't change the direction, dir is nothing else but camera direction of the provided camera. Now the undefined variable is single float. Of course, in this case, again, we have to quote it, since make array is a function and not a macro. Quit this, compile it once again. Okay, 0 warnings, 0 nodes and 0 errors. We're fine with that. Now we're almost finished with all the camera related stuff. This function was only to change basically from world to view coordinates, and now we can go and talk about the intersections of array and a sphere.